Today's math lesson on an intro to dilations or transformations of shapes. Our do now is an equation is shown below. 3x plus 4 is equal to 9x minus 8. Which value of x makes the statement true? So as you can see, there's variables on each side. There's 9x and then 3x. And so I'm going to first rewrite the equation. We have 3x plus 4 is equal to 9x minus 8. I'm going to first move the 3x to the right side. So to do that, the opposite of adding 3x is subtracting 3x. So I'm going to subtract 3x on both sides. 3x minus 3x is 0, so then I'm left with 4 is equal to 9x minus 3x is 6x minus 8. Now I want to move my constants to the same side. So I move my variables to one side, and I have to move my constants, in this case, -8, to the left side. So to do that, the opposite of subtracting by 8 is adding 8. Four plus 8 is 12. So then we have 12 is equal to 6x. Our second zero pair was -8 plus 8. And now we have to move the 6 to the other side. So we want to isolate the variable. We want to get the x alone. And to do that, we're going to divide both sides by 6. 6 divided by 6 is 1. So we have x is equal to 12 divided by 6 is 2. So our answer is going to be C, 2. And what we can do is we can plug this in to the equation to make sure that it makes sense. So 3 times 2 is 6. 6 plus 4 is 10. 9 times 2 is 18. 18 minus 8 is also 10. So that's how we can check to make sure that 2 is the correct answer. Today's TEK is 8.3b, and we will compare and contrast the attributes of a shape and its dilation on a coordinate plane, and our DOL is given 4 problems. I will compare and contrast the attributes of a shape and its dilation on a coordinate plane with 100% accuracy. So we have a few vocab words to go over. This visual didn't show up, but it just showed an example of a dilation. So maybe the smaller blue triangle was the original image, and then the green, bigger triangle is the dilated image. So it was enlarged. Or we can flip it around, and let's say that the green, bigger image was the original image, and then the blue, smaller triangle is the dilation. So then it shrunk. So corresponding sides are the sides that are the same on the two shapes. So these shapes are similar figures. Dilations are similar figures because they have the same shape. They're just different sizes. The corresponding vertices are the angles. And corresponding vertices in similar triangles are the same. So they're congruent angles. Again, dilations make proportional figures because there's usually a scale factor, which we'll get into finding today. And we can usually write an algebraic rule or expression, which will look something along the lines of x comma y. And then we'll have a number x comma another number y. Figures can be dilated around the origin, which is that 0, 0 point on a coordinate plane, or sometimes they have other centers of dilations. So starting off with this journal, it says square ABCD, which is the smaller blue square, was dilated with the origin as the center of the dilation to create ABCD. We have to first determine the coordinates of the vertices as well as its dilated side. So the success criteria for today is that I can generalize the ratio/scale factor of corresponding sides of similar figures. We're going to get into why ratios and scale factors are the same thing. I can identify the scale factor of corresponding coordinates of similar figures, and I can write an algebraic rule for a dilation. So starting off with our pre-image, which was our original image, I'm going to list out the points or the coordinates. So for side A, it's 1, 1, or point A, I mean, not side A. For B, it's -1, 1. For C, it's 1, -1. For D, it's -1, -1. Then I'm going to list out the coordinates of the dilated shape. So for the reflected or dilated A, we have 3, 3. For the dilated B, we have -3, +3. For dilated C, we have 3, -3, +3, -3. And then for D, we have -3, -3. To figure out what the scale factor is, I have to figure out by what number the corresponding points have changed, right? So 3 divided by 1 is 3. 3 divided by 1 is 3. So it looks like our scale factor would be 3. So let's go ahead and check that with some of the other corresponding coordinates. So we have for B, it's -1, +1. For dilated B, it's -3, +3. So if we multiply -1 times +3, we get -3. If we multiply 1 times 3, we get 3. So our rule is going to be 3x, 3y. Another way to solve for the algebraic rule for the dilation is to figure out the side lengths. So for example, the length from B to A is 1, 2, 3, 4, 5, 6. The length from the original B to A is 2. Then we find the ratio, so 6 divided by 2 is 3, which is, again, the same thing as a scale factor. So that makes our rule still x y to 3x, 3y. And as you can see, when our coefficients are greater than 1, our shape has been dilated to be enlarged, so it's been made bigger. So again, a dilation is a transformation that produces an image that is the same shape as the original, but is a different size. A dilation that creates a larger image is called an enlargement. A dilation that creates a smaller image is called a reduction. A dilation stretches or shrinks the original figure. And sometimes when the shape is dilated from the origin, it looks like it's been shifted over instead of one shape is inside the other shape. So for this IG problem, we're going to find the scale factor of the dilation. So we're going to use the coordinates to find the lengths of the sides of each triangle. So we're going to do the method, the second method that I introduced from that journal, where we're going to find the side lengths. So for A to C, that's 2. For C to B, that's 3. And this method works best if you can easily count how long the length is because it's on the grid nicely. There's going to be some dilated shapes that are not easy to figure out what their side length is without doing some math calculations. So in those cases, it might be better to figure out what the original coordinates are and then the dilated coordinates and figure out the rule from there. Okay, for the dilated A to C, we have 4. And then for the dilated C to B, we have 6. So now we're going to find the ratio, which is going to lead us to the scale factor of the corresponding sides. So the dilated A to C was 4. The pre-image A to C was 2. 4 divided by 2 is 2. Then for dilated C to B, we have 6. For pre-image or original image C to B, we have 3. 6 divided by 3 is 2. So the scale factor of the dilation is 2. And our rule is going to be x comma y to 2x comma 2y. So again, because our coefficients, remember the coefficients are the numbers in front of variables, is greater than 1, our image was enlarged or made bigger. For the second I do, we have to tell whether one figure is a dilation of the other, and we have to explain our reasoning. So we have quadrilateral MNPQ has side lengths of 15 millimeters, 24 millimeters, 21 millimeters, and 18 millimeters. Quadrilateral of dilated MNPQ has side lengths of 5 millimeters, 8 millimeters, 7 millimeters, and 4 millimeters. So I'm going to find the ratio, which is going to lead me to find the scale factor. So 15 divided by 5 is 3. 24 divided by 8 is 3. 21 divided by 7 is 3, so far it's looking good. And 18 divided by 4 is not 3. So actually, quadrilateral of M and PQ is not a dilation. Because the scale factor or because not all of the corresponding side lengths have a scale factor of 3. This would have been a lot faster if I could have typed it in instead of writing it out. Then it says triangle RST has angles measuring 38 degrees and 75 degrees. Triangles of dilated RST has angles measuring 67 degrees and 38 degrees. So right away I know that this is not a dilation because dilated figures have congruent angles. So something to know, a trick for the rule, is that if the coefficient is less than 1, it's going to shrink the original figure. And if the coefficient is greater than 1, like we've seen, it's going to enlarge the figure. So this understanding of the coefficient being either less than 1 or greater than 1 and how it will change the dilated shape is important to know. Now it's time to demonstrate your learning with a 4-question DOL. Thank you so much for following along in today's math lesson, and see you in the next math video. Bye.